Hello everyone. Welcome back to Unit 2 Chemistry. Today we look at two superpowers of water. First, why water dissolves so many substances. Second, how to calculate the heat energy water absorbs. Don't worry about that formula yet. We will build it slowly, piece by piece. Take a breath. Let's begin. Let's start with a question. Why does salt vanish in water but oil just floats on top? The answer is one word. Polar. Polar just means the molecule has two different ends, a slightly positive end and a slightly negative end. That's all it means. Think of every water molecule as a tiny, weak magnet. The oxygen side is the negative end. The hydrogen side is the positive end. We write a small delta minus on the oxygen. Delta just means slightly negative, and a small delta plus on each hydrogen, slightly positive. Now here is the golden rule of solvents. Like dissolves like. Water is polar, so water dissolves many polar substances and many ionic substances. Ionic means made of charged particles like salt. Charges attract charges. Oil is non-polar. It has no charged ends. Water's tiny magnets have nothing to grab, so oil is left alone. One warning. You will hear people call water the universal solvent. That is not correct, and it can cost you a mark. Water is a very good solvent. It is not a solvent for everything. Some ionic solids, like silver chloride and calcium carbonate, barely dissolve at all. So say it carefully. Water dissolves many ionic and polar substances, not all of them. See it on the right. Salt in, salt gone. Oil in, oil floats. Quick check. Why does the oil float untouched? Because it's non-polar, and like dissolves like. Good. Now two words that sound similar, but are not the same. This trips up a lot of students. Let's fix it now. Dissolving means the particles spread out evenly through the water. That's it. Sugar dissolves. But every sugar molecule stays in one piece. It just floats away, whole, like a boat drifting off. See the top picture. One whole sugar molecule, surrounded by water. Nothing broke. Dissociation is different. Dissociation means the substance splits apart into its ions. Ions are just charged particles. Salt is sodium chloride. In water it splits. One positive sodium ion, one negative chloride ion. The little AQ means aqueous, which just means dissolved in water. Bottom picture. The salt crystal breaks up. The ions drift apart separately. Quick check. Does sugar dissociate? No. Sugar only dissolves. Salt does both. It dissolves and it dissociates. Lovely. So the ions have split apart. What happens to them next? Water surrounds them, like fans crowding around a celebrity. That crowd of water molecules has a name, a hydration shell. A shell of water wrapped around one ion. And the crowd is not random. It obeys one simple rule. Opposites attract. Look at the sodium ion. It's positive. So which end of water turns to face it? The negative end, the oxygen end. Every water molecule points its oxygen at the sodium. Slightly negative oxygen, hugging the positive ion. Now the chloride ion. It's negative, so water flips around. The slightly positive hydrogen ends face inward. The oxygens face away. Quick check, and this one is a favorite exam question. Which end of water faces the chloride ion? The hydrogen end. And which end faces sodium? The oxygen end. If you got both, brilliant. And here's why it matters. Those shells act like bodyguards. They stop the ions rejoining. That is how salt stays dissolved. One more job for water. It's not just a solvent, it's a meeting place. A reaction medium just means the environment where a chemical reaction happens. In a solid, particles are locked in place. They can't meet. But dissolved in water, they're free. They move, they bump into each other, and they react. This is why so much of the chemistry in your body happens in water, your blood, your cells, and most of the reactions you'll run in a school lab. Watch the right. Two dissolved substances meet in water and form something new. Water often enables dissolved particles to move, collide, and react. Not every reaction needs water, and water doesn't force a reaction to happen. But for a huge number of reactions, it is the medium that lets them get started. Now for water's second superpower, absorbing heat. And here is the only formula you need today. Q equals m times C times delta T. 4 symbols. Let's meet them one at a time, slowly. Q is the heat energy, measured in joules. A joule is the standard unit of energy, like a dollar is a unit of money. M is mass. How much stuff you're heating, in grams. Careful, grams, not kilograms. That catch costs marks every single year. C is called specific heat capacity. Big name, simple idea. It's how much energy 1 gram needs to warm up by 1 degree. Think of it as how stubborn a substance is about heating up. For water, C is 4.18 joules per gram per degree. Memorize that number, 4.18. Delta T is the change in temperature. Delta is just the maths symbol for change in, and change always means the same thing. Where you finished, minus where you started. Final minus initial. One condition, and write it down. This formula works while the temperature is changing and the substance stays in the same state. Liquid water staying liquid water. If it's melting or boiling, that's a different formula and a different lesson. Quick check. Water goes from 20 to 50 degrees. What's delta T? 50 minus 20, 30 degrees. If you said 30, you're ready for the examples. Now, 4.18 is a huge number. Water is one of the most stubborn substances on Earth to heat up. Why? Hydrogen bonds. These are attractions between water molecules, weak little handshakes from one molecule to the next. See the dotted lines on the right. Those are the hydrogen bonds between molecules. The solid lines inside each molecule are the OH bonds, and those are strong polar covalent bonds. Between and inside. 2 different things, and examiners check that you know it. So when you heat water, the energy has 2 jobs. Some of it speeds the molecules up, and that's what raises the temperature. Some of it goes into weakening all those handshakes. Because the energy is shared out like that, you need a lot of it for each single degree. Water is a giant heat sponge. Compare it with iron. Iron C is about 0.45. Water's is 4.18, nearly 10 times more stubborn. Where do you see this in real life? 3 places. 1. The coast. The ocean warms slowly in summer and cools slowly in winter. So coastal towns get mild weather. Inland towns swing hot and cold. 2. You. Your body is mostly water. That water resists temperature change, which helps hold you steady at about 37 degrees. 3. The kitchen. Ever waited forever for a pot to boil? That's 4.18 in action. But once hot, water holds its heat and cooks food gently and evenly. Coast. Body. Cooking. 3 examples, ready for your exam. Now let's calculate. Example 1. The basic version. We'll go step by step, and we'll use these same steps every time. How much heat do we need to warm 250 grams of water from 20 degrees to 65 degrees? Step 1. Write down what we're given. Mass, start temperature, final temperature, and C for water. Step 2. What are we finding? Q, the heat energy, in joules. Step 3. The formula. The water stays liquid the whole time, so we're allowed to use it. Step 4. Check the units. Mass is already in grams, temperature's in degrees, nothing to convert. Lovely. First find delta T, final minus initial. 65 minus 20. That's 45 degrees. Now substitute with every unit shown. 250 grams times 4.18 times 45. Multiply it out. 47,025 joules. Our data has 3 significant figures, so we round to 3. 47.0 kilojoules. Box the answer. 47.0 kilojoules. Last step, always. Is it reasonable? A cup or so of water warmed a fair way. Tens of kilojoules. Yes, that's sensible. Tick. Example 2. Same formula, driven backwards. This time we know the energy, and we want the temperature change. 500 grams of water absorbs 33.4 kilojoules. How much does the temperature go up? Given. mass, energy, and C. Find delta T. Rearrange the formula. Divide both sides by m times C. Delta T equals Q over mc. Now the trap. The energy is in kilojoules, but our formula needs joules. Kilo means 1000, so 33.4 kilojoules is 33,400 joules. Never skip this step. Substitute with units. 33,400 joules divided by 500 grams times 4.18. The bottom is 2090. Divide. 15.98 degrees. 3 significant figures. 16.0 degrees. Box it. A rise of 16 degrees. Reasonable? Half a kilogram of water, a decent chunk of energy, a modest rise of 16 degrees. Yes, that fits. Tick. Example 3. A classic. Taking water all the way to boiling point. How much energy does it take to warm 1.5 kilograms of water from 20 degrees to 100 degrees? Given. Mass in kilograms. Start and finish temperatures. And C. Find Q. Formula. Same friend as always. Spot the trap. Mass is in kilograms. The formula wants grams. 1.50 kilograms is 1500 grams. Delta T. Final minus initial. 100 minus 20. 80 degrees. Substitute with every unit. 1500 grams times 4.18 times 80. That gives 501,600 joules. Round to 3 significant figures. 502 kilojoules. Box it. About 500,000 joules. Reasonable? It's a much bigger mass than example 1 and a much bigger temperature climb, and the energy is roughly 10 times bigger. That scales sensibly. Tick. And one important note. This energy takes the water up to 100 degrees. It does not turn it into steam. Reaching 100 degrees is not the same as boiling it away. Changing liquid into steam needs extra energy on top, and that's our next lesson, latent heat. Example 4. A thinking question, the kind VCE examiners love.
Equal masses of water and iron. Each absorbs exactly the same energy, 4,180 joules. Which one gets hotter? Have a guess before I show you.
Given. Same mass, same energy. Only C is different. Find delta T for each substance. Formula, rearranged like example 2. Units are already grams and joules, so no conversion. Water first. 4,180 divided by 418. Exactly 10 degrees. Now iron. 4,180 divided by 45. About 93 degrees. Same energy, and the iron is scorching. Box the idea. Iron's temperature jumps about 9 times higher because its heat capacity is about 9 times smaller. Small c means easy to heat. Big C means stubborn. Reasonable? 4.18 divided by 0.45 is about 9.3, and 93 is about 9.3 times 10. The two answers agree with each other. Tick. Now one thing to be careful with, because it gets muddled all the time. When a metal spoon in hot soup burns your fingers, the main reason is thermal conductivity. That means how quickly heat travels through a material. Metals move heat very quickly. Specific heat capacity is a different property. It's how much energy 1 gram needs to rise by 1 degree. So what has this calculation actually shown? It has shown that for the same mass and the same energy in, the substance with the smaller specific heat capacity ends up much hotter. That's the conclusion. Keep the two properties in separate boxes in your head. Last example, the hard one. Real life with real messiness. Stay with me, we'll take it in small steps. A 2,200 watt kettle, only 85% efficient. How long does it take to heat 1.2 kilograms of water from 18 degrees up to 100? Two new words first. A watt is 1 joule per second. So this kettle pushes out 2,200 joules every second. Efficient means how much of that energy actually reaches the water. 85% goes in. The other 15% leaks away as sound and warmth into the kettle body and the air. See the arrows. Input energy from the wall. Most goes into the water, some escapes. Keep those two amounts separate in your head. Useful energy and input energy. They are not the same number. Given. Power, efficiency, mass, start and finish temperatures. Find. Time. In seconds. Our plan. 3 steps. First, the useful energy the water needs. Second, the input energy the kettle must draw. Third, the time. Convert the mass. 1.20 kilograms is 1,200 grams. Step 1. Delta T. 100 minus 18. 82 degrees. The water needs 1200 times 4.18 times 82. That's 411,312 joules of useful energy into the water itself. Step 2. But the kettle is leaky. To deliver that much, it must draw more from the wall. Divide by the efficiency, 0.85. That's 483,897 joules of input. Notice the input is bigger than the useful energy. It always is. Step 3. Time equals energy divided by power. 483,897 divided by 2,200 joules per second. 219.95 seconds. 3 significant figures. 220 seconds. That's about 3 minutes and 40 seconds. Box it. 220 seconds. Reasonable? Go and time your kettle at home tonight. A full kettle takes a few minutes. Our answer says 3 minutes 40. Spot on. Tick. And notice the last line. This is the time to bring the water up to 100 degrees. It does not include boiling it away. If you followed all 3 steps, you just solved a genuine ATAR level question. Well done. Let's lock it in. 6 lines. Water is polar. Negative oxygen end, positive hydrogen ends. Like dissolves like. Water dissolves many ionic and polar substances. Not everything. And ionic compounds don't just dissolve, they dissociate into separate ions. Hydration shells. Oxygens face the positive ion. Hydrogens face the negative ion. Opposites attract every time. The formula. Q equals mcΔT. Final minus initial. And only while there's no change of state. Water's C is 4.18. Huge because of hydrogen bonds between the molecules. That's the coast, your body, and your kitchen. And the habit. Convert units. Show units. Round properly. Box the answer. Then ask, is it reasonable?
Your turn. Pause the video here. Write these 5 out and give every one of them a real attempt. Then, press play again, because the full solutions are in the next few boards right after this. 1. A hydration shell around a potassium ion. Think about the charge first. 2. A basic Q calculation. 3. Backwards like example 2. Watch the kilojoules. 4. A written explanation. Use the words specific heat capacity and hydrogen bonding. 5. The full kettle method. 3 steps. You know them now. Pause here. Solutions time. Question 1. The hydration shell around a potassium ion. Step 1. Look at the charge. Potassium ion, K+. It's positive. Step 2. Our rule. Opposite charges attract. Step 3. Which end of water is negative? The oxygen end, delta minus. So every water molecule turns its oxygen inward, toward the potassium. The hydrogens point outward, away from it. Box it. Exactly the same picture as sodium, because both ions are positive. If you drew the hydrogens facing inward, that's the chloride arrangement. Flip it, and you've got it. Question 2. Find Q for 350 grams of water, heated from 15 degrees to 55. Given. Mass, both temperatures, and C for water. Find Q, in joules. Formula. No change of state, so we're clear to use it. Units. Already grams and degrees, nothing to convert. Delta T, final minus initial. 55 minus 15, 40 degrees. Substitute with units. 350 grams times 4.18 times 40. That's 58,520 joules. 3 significant figures. 5.85 times 10 to the 4. Box it. 58.5 kilojoules. Reasonable? A bit more water than example 1, a similar temperature climb, and an answer in the tens of kilojoules. Tick. Question 3. 750 grams of water absorbs 62.7 kilojoules. Find the rise in temperature. Given. Mass, energy, and C. Find delta T. Rearrange. Delta T equals Q divided by M times C. Convert first. 62.7 kilojoules is 62,700 joules. This is the step people forget. Bottom of the fraction. 750 times 4.18 is 3,135. Now divide. 62,700 divided by 3,135. That comes out at exactly 20 degrees. 3 significant figures. Write it as 20.0 with the point 0. Box it. A rise of 20.0 degrees. Reasonable? Compared with example 2, roughly double the energy going into about 1.5 times the mass. A bigger rise makes sense. Tick. Question 4. The written one. 5 marking points, so build your answer like this. Why do bayside suburbs have milder nights than inland suburbs? Point 1. Water has a high specific heat capacity, 4.18 joules per gram per degree. Point 2. That high value is linked to hydrogen bonding. Energy is needed to weaken the hydrogen bonds between water molecules, not only to speed the molecules up. Point 3. So during the day, the bay stores a large amount of energy for every single degree it warms by. Point 4. Then at night, it cools slowly and releases that stored heat gradually into the surrounding air. Point 5. The result. The air near the bay changes temperature less than the air further inland. Land has a much lower heat capacity, so it warms fast, cools fast, and the inland night gets colder. Box it. High specific heat capacity plus a gradual release of stored heat gives a smaller drop in temperature overnight. Use the words specific heat capacity and hydrogen bonding, and you'll pick up the marks. Question 5. The kettle. Same 3 steps as example 5. An 1800-watt kettle, 90% efficient, heating 1 kilogram of water from 22 degrees to 100. Given. Power, efficiency, mass, and the 2 temperatures. Find the time in seconds. The plan. Useful energy. Then input energy. Then time. Convert the mass. 1 kilogram is 1,000 grams. Step 1. Delta T. 100 minus 22. 78 degrees. Useful energy. 1,000 times 4.18 times 78. That's 326,040 joules going into the water. Step 2. The kettle only delivers 90%, so divide by 0.9. The input energy is 362,267 joules. Bigger than the useful energy, as always. Keep the 2 numbers separate and labelled. Step 3. Time equals input energy divided by power. 362,267 divided by 1800 joules per second. 201.26 seconds. 3 significant figures. 201 seconds. Box it. 201 seconds, which is 3 minutes and 21 seconds. Reasonable? It's quicker than example 5, and it should be. Less water and a more efficient kettle. Tick. And the last line again. This brings the water up to 100 degrees. It does not boil it away. That's latent heat, and that's next lesson. If all 5 of those worked out for you, you are in very good shape. Great work today. Water dissolves so much of the world around you, and it holds temperatures steady while it does it. Next lesson, latent heat, where we finally turn that boiling water into steam. See you there.